Um, Good morning and welcome to the last lecture in this course. So in this lecture we are going to consider yet another blockchain related topic. So we have finished with the sequence of use cases, and the last lecture is dedicated to yet another technological topic of blockchain-based storage. And we also will take a quick look at the future perspectives when it comes to research in blockchain. So blockchain-based storage, it's diverse, it's and the numerous. So what you can see here, IPFS, Storage, Swarm, SIA, Filecoin, Safe, and Arweave are probably the main ones, but there are also quite a few additional systems. So they're diverse in the sense that they provide different functionality. So each one, they are not mutually interchangeable, and each one pursues a slightly different purpose. Some additional systems which I am not mentioning are integration of a database with blockchain. So there are systems that orient themselves in that direction. So the very first attempt, or successful attempt, the very first system of storage based on blockchain is called the Interplanetary File System, or IPFS. So the name is a bit presumptuous, as you can see. So the idea of IPFS is to link decentralized data together. So the assumption is that pieces of data, chunks of data if you want, are stored inherently in different locations, and we need to find them and link them together, and this is what the system is doing. It's maintaining the linkage between different pieces of information. So the data is assumed to be immutable. If you want to update the data, you can do it, but you do not replace the old data. You just create a new piece of data and you put it elsewhere. And you can just rearrange the links. But the old piece of data is not being modified. The addressing is content-based. What does it mean? It means that the addressing never goes by locations or endpoints. The location always goes by names and hashes of the data. So we are going to see how IPFS implements this functionality. IPFS uses blockchain for two different purposes. First, it uses blockchain internally. So individual nodes may be incentivized to store pieces of data. So there are monetary incentives. So if you want someone to store a piece of your data, you may want to pay that someone. And in fact, they came up with their own cryptocurrency named Filecoin. And IPFS may be supported by Filecoin. However, the connection is modular, so you can use IPFS without Filecoin if you want, or you can integrate it with Filecoin. Now, the second way in which blockchain is used in IPFS is to secure the hashes. So the whole structure, after created, can be secured by hashes of all the links, and those hashes can be stored on the chain. This is usually what the application built on top of IPFS is doing. So it's not the functionality of IPFS itself. IPFS only provides those hashes, but the application built at top could store those hashes on the chain. This is not mandatory. I mean, it's up to the application. And the design, which we are going to discuss soon, borrows ideas from all technologies of BitTorrent, Git, and Kademlia. So Git is a file versioning tool, and while BitTorrent and Kademlia are systems for, well, that like Kademlia is a DHT, so distributed hash table, well used in the context of peer-to-peer file sharing, but in general the DHT is used for finding locations of individual pieces by names or caches. And BitTorrent is a system for file sharing, which uses some sophisticated ideas about how the different files can be exchanged in the most efficient way. And those ideas are used in IPFS. So IPFS elements are the following. It has the concept of IPFS identities. So we need to manage node identity generation and verification that is the correct identity, that the node is not trying to falsify someone else's identity. Network manages connection between the peers using various underlying network protocols. So it's the same as in peer-to-peer networks. Routing maintains information to locate specific peers and objects. So it defaults to an DHT based on Kademlia, but it's possible to use something else. The exchange protocol is how those pieces of information being transferred over the network. So they develop their own block exchange protocol or chunk exchange protocol. It's not exactly maybe right to call it blocks because it's not blocks in the same way you would call blocks on chain. So chunk exchange protocol called BitSwap that governs efficient chunk distributions. In fact, it's modeled as a market where you can sell your space, storage space, and where you could pay for someone storing your data. Objects, I'm going to discuss it soon. So an object in IPFS is modeled by a Merkle DAG of content addressed immutable objects with links. And it's used to represent file hierarchies and in general arbitrary data structures. So files are versioned using file system hierarchy similar to Git. And finally, there is the naming component which provides self-certifying mutable name system. So let's delve deeper into Merkle DAGs in IPFS. A Merkle DAG in IPFS basically consists of different chunks of information. So each node is a chunk of information. And then there is a link. So there is a top of the hierarchy of the file system. And from there, you can have folders, but folders not in the direct sense of the file system. It could be rather collections of information. So the links are not like not links of the operating system. It's more like high-level URLs with some additional security guarantees. And it's a DAG, it's not a tree, right? Because the same chunk can be referenced from multiple chunks at the upper level, from the multiple vertices at the upper levels. So each link contains 3 pieces of information: name, hash, and size. All are used for the purpose of verification, but the name and hash are also used to physically locate the chunk from which data can be downloaded. So let's take a look at an illustration of what happens with the Merkle DAG when the file is being modified. So as mentioned, the old version doesn't disappear, a new version is created, but how to do it in the most efficient way. Okay, so suppose that we have some file F, which is broken into 2 chunks, A, B, C, D, and like set within each chunk there is a further division into A, B, and C and D. So A, B, C, and D. A, B, C, D, and then A consists of A0, A2, A2, B0, B1, B2, C0, C1, C2, D0, D1. Okay, so that's the initial situation. Now, let's assume that we want to modify the file by changing D, so now D becomes D prime, and also appending EF at the end. How would it affect the Merkle diagram? So as you can see, this part is not affected at all. This part is not affected at all. Now here, what do we change under D? We add another chunk, D2, to the previous chunks, D0, D1. So we simply add it here as another leaf and recalculate the leaf. And here we also have to create a new vertex, because the old one cannot be used any longer. Now here we simply add the entire subtree and we link it here to the upper level. And of course the upper level also has to change because of that. So as you can see, this part would be changed. This part would be changed, this part, this vertex, and here the entire subtree would be added. So what's the main point? The main point is that those can still be reused and linked from both the old version and the new version. Okay, so that's about IPFS. The next system I would like to talk about is Swarm. Swarm is built by Ethereum, and it uses Ethereum-specific elements. It also uses content-based addressing. However, its philosophy is different. In IPFS, we are trying to link pieces of information which is already stored and which already mostly exists in the system. Well, we can increase the amount of replication, but in principle, IPFS doesn't try to rearrange the storage. It only aims to link existing storage pieces. In Swarm, it's the opposite. In Swarm, we want to place files, and we decide on the location of placement based on the files. So the assumption in Swarm is that the storage doesn't exist initially. We need to take care of it. Okay, how does Swarm do that? It also uses content-based addressing, but differently from IPFS, the hash determines the location. So in Swarm, you calculate the hash of the data, and based on the hash of the data, you determine, like using DHTs, you determine on which of the many nodes in the network the data will be stored. Mutability is supported by version in the same way as IPFS. And Ethereum name service is used for finding the mutated files. The system is implemented, the whole system, or at least most of the system, the name service and some other functionalities are implemented as a contract at top of Ethereum. And like IPFS, it also uses a DHT Academia for the communication. Swarm additionally provides an incentive layer where nodes can buy chunks of data, of stored data, but also where nodes can be paid or incentivized by storing additional replicas by paying. So, for example, you calculate the hash. You decide that based on the hash the data needs to be stored on that particular node. The node needs to be incentivized, and the nodes are incentivized by earning Ether. So it's highly integrated with Ethereum. This is conceptual overview of Swarm. So first, okay, so suppose the user wants to add some data to the network. So this is the network. Okay, what does the user do? First, it creates a tree it breaks the file into chunks and creates a trio, cryptographic tree of those chunks. And then, based on the hashes, each chunk would be placed on a different vertex in the network. And of course, those vertices need to be incentivized. So obviously there are a lot of hashes, like to verify the consistency. And later, when someone needs to find the data, it would send the request, and then it would need to collect the chunks, individual chunks from individual nodes in the network, and then put them together and restore the original file. The next system we are going to consider is called Store.j. Store.j is, again, a bit different. In Store.j, there are three types of nodes: satellite storage and uplink nodes. Uplink are just the users who want data stored or who want to retrieve the data. So they just called uplink in Store.j. But the satellite and storage nodes. So storage nodes are storing the data, while satellite nodes are responsible for the organization of the overlay of the network of storage nodes. So they're configuring the storage nodes. Now, Store.j assumes that most nodes are rational. Rational meaning not Byzantine. They are not trying to bring the system down. So they are not aiming to tolerate one third of Byzantine nodes. That's not their goal. But they are also not assuming that nodes are just altruistic and following the protocol no matter what. They assume that nodes would be doing what they are doing for the personal gain. Now, in Store.j, Store.j puts emphasis on privacy, so all the data is encrypted. Another interesting distinguishing feature of Store.j is high degree of redundancy and resilience to tampering. How do they do it? They use KN Reed-Solomon erasure codes. So what is a KN erasure code? We break, it's not even correct to say that we break a file into chunks. We take the entire file and we build pieces of information out of the file. But pieces of information are not just chunks. They are overlapping with each other. So we build, given a file, we build n pieces of information. But of those n, we need only k, and k is smaller than n, in order to restore the original file. So there is some degree of redundancy involved. So why do we do that? Because we assume that not all n pieces will be available. Maybe some of the nodes will be down, and we won't be able to retrieve the pieces. This is why we want some degree of redundancy. We assume that not all n pieces would be available, but we don't need all n, we need only k, which is a smaller number. And then all n pieces would be stored on different nodes in the network. Additionally, Store.j uses an incentive system with node audits, and Store.j also maintains a reputation of individual nodes, which is collected. So for example, it's not enough that someone says, oh, like I didn't get a chunk from that node. So a reputation system would be collecting votes and ranks from different participants, and if many participants rank the same node as misbehaving, then this is what would be reflected in the reputation system. So here's a conceptual overview of storj. So given a file or piece of information, we build what's called stripes, and from that we build erasure codes, right? And then we distribute the erasure codes in a different way over the network. So after we have the codes, we need to decide about the right place for each code. And here you see the network. So there is one satellite node. Those nodes are simply representing the user, right? So they are user nodes, or uplink nodes in their terminology. And those are the storage nodes, which constitute the majority of the network. So we can also build different taxonomies of blockchain-based storage systems. So here in this slide, we see the taxonomy based on the underlying network. Some of the systems are using structured network based on DLTs, while some other systems are using unstructured network. And in unstructured network, we typically just there is no, like the topology of the network is self-organizing and maybe like chaotic, not following particular structure. That's why it's called unstructured. And usually, in order to find something in an unstructured network, you need some discovery mechanism, usually done by partial flooding, but also could use DLTs for more specific purposes. A different topology is that of incentive mechanisms in storage-based systems. So which incentive mechanisms do we have? We can reward the node for storing information. We can punish the node for not behaving properly. We can charge the node for uploading and propagating pieces of data. Sorry, the other way around. The node can charge, if the node participates in the propagation of data, not just storage, but also propagation, it may expect a reward and charge certain fee for doing that. There could be some trade of data, like I'm selling you this piece of data for that much, so it's like a marketplace. And of course, sometimes like retrieval, if I want to retrieve some piece of data, I need to pay for that as well. Not all mechanisms exist in all systems. You can see that some of the systems would appear in multiple places here because they implement different mechanisms, but there is not one system which implements all of the mechanisms. Again, there is diversity between the systems. Okay, so this concludes the brief overview of blockchain-based storage today. And the second part is the outlook towards the future directions. So generally speaking, people believe that blockchain will be used, like it will not conquer the world, but it will be used as a dedicated technology and part of the bigger infrastructures, but especially in application domains related to energy markets and trading, digital currency and finance, agreement-driven healthcare provision, and record keeping. And of course, record keeping is also a very big domain, right? So you have identity, IP rights, digital rights, lender registry, supply chain. We've seen a lot of use cases related to that. So in one of the directions of future research, of course, is to continue developing this ecosystem and also understanding what blockchain is good for and what blockchain is not good for and how to use it in the most optimal way. So far, there is like by the count, we are now in blockchain 4.0, but of course it's like the division is arbitrary. So what can we expect in blockchain 4.0 or any future type of blockchain? What challenges remain and what challenges will arise in the future? We already talked about many of those challenges, so scalability in terms of the storage, number of participants and throughput rate, interoperability, which consists of bridges between competing blockchain systems, and variety of atomic swap procedures with different trade-offs, privacy in blockchain applications, including zero knowledge and other techniques, new proof of something schemes, and better protection against attacks, especially these days. Perhaps the MEV attacks are the most intensively explored topic in security of blockchain. Additionally, in some companies offer blockchain as a service in the cloud. So we have infrastructure as a service, we have platform as a service, we have application as a service, but they are also offering to make blockchain as a service. So Microsoft, for example, is offering this. However, it's interesting how you meter the use of blockchain, right? Because significant part of offering something as a service is metering. So in infrastructure, we measure the consumption of storage, the consumption of computation, the consumption of bandwidth, and then we charge for those, for exactly the amount of resources consumed. So how do we do it with blockchain? So already there are some suggestions, but this is still developing. Smart contract enhancements are again like multifold. So the languages are still developing. The idea of how to execute contracts is still developing. How can we make the contract execution obviously more efficient and cheaper? How to integrate contract execution with trusted execution environments, that's another area. And how to build tools for debugging and testing smart contracts. So all those areas are being explored. Speaking about tools, so tools of course exist in the context of smart contracts, but they also exist, or they are also important in other contexts. So for example, I already talked about blockchain simulators and generator of synthetic workloads, and there are also emulators which are different from simulators, right? Integrators and composers. So under Hyperledger, some of the projects are about how we build applications with focus on integrating blockchain as individual components. So this kind of compositional tools also being developed. Recipes and design patterns. So as different pilots and use cases continue to emerge, we gather better understanding about how to integrate blockchain within infrastructures of real life scale and complexity, what to store on chain, what to store off chain, and how to provide the end-to-end verifiability. And in the context of POW especially, but in general, there is a question of sustainability of blockchain, green blockchain if you want, which was originally inspired by the fact that Bitcoin is consuming so much energy. So I'm going to expand a bit about the last part. sustainability of blockchain. So one direction on the sustainability of blockchain is to replace crypto puzzles in the context of POW with useful computation. But the problem of crypto puzzles is not only do they burn such amounts of energy, but also finding a solution to the crypto puzzle doesn't benefit humanity as a whole whatsoever. It only benefits the miner who got the reward, and maybe benefits the blockchain ecosystem in the sense that we make progress and the chain becomes longer. But the solution to the crypto puzzle itself is not like a solution to any important problem for humanity. Okay, so the idea here is to replace crypto puzzle with some useful computation, and people have been exploring this idea from 2013, where the first idea of Prime coin came out, Prime coin, then Gap coin, and then a lot of different attempts from 2017 until 2023. So what are they trying to do? What are the type of tasks they consider as candidates for replacement of crypto puzzles? Well, mostly they consider machine learning, optimization problem, linear algebra problems, and also and also prime number decomposition or factoring of prime numbers, like in cryptography. Those are the 4 most popular classes of tasks explored as in the context of replacing crypto puzzles. So for machine learning, there are works that focused on deep learning, neural networks, and others. For linear algebra is it's interesting because linear algebra is easier, not as hard as other classes on this list. So how can we use it? Well, we can use it if we make the matrices on which we perform the computation big enough. The problem with this approach is that in order to build a hard instance, we need significant amount of storage for storing the matrices. A similar problem arises in the context of machine learning, where we need large data sets. So which usually it means that data sets themselves cannot be stored on chain. So we have to store it off chain and just integrate the off chain storage with the on chain storage by securing the hashes. So optimization problems again multifaceted. So there is the traveling salesman problem, but there are local search problems. Some of them we're exploring the SAT problem. Yeah, quite a variety under optimization problems. So how do we extend support to, how do we extend the architecture of Bitcoin to support useful tasks? So here again you see the standard layers, and in the standard layers, like this is consensus layer or data manipulation, this is storage layer. Those two layers are affected by the replacement. Now the main changes here, what you can see is like those colored boxes are the changed information. So the POW mechanism is changed, block validation is changed, block storage is changed, transaction pool needs to be updated with respect to the class of task being used. But there is also a new box here. There is a need to maintain supply of tasks. So crypto puzzles can be generated on the fly by the miner, while useful tasks need to come from somewhere. So who is going to supply them? Then one model is to introduce dedicated suppliers in the system. The other model is to say that any instance of a particular class of task is considered to be interesting. But in this case, the utility would be more limited compared to the case when a supplier provides the useful instance. How do we define the utility, right? So what's the status of this direction of research, of replacing crypto puzzles by useful classes of tasks? So it turns out that despite the numerous attempts, no one has been able to achieve all the guarantees of crypto puzzles, while the research is still ongoing. And the reason for that is the multiplicity of requirements. So crypto puzzles appear very simple. So when we looked into this, we were amazed to discover how many different properties crypto puzzles satisfy that are essential in the context of POW. So what are the properties? Well, we need to be able to solve crypto puzzles fast. Crypto puzzles need to be hard enough. If they are not hard enough, that the blocks will be produced too fast. But on the other hand, not too low, because otherwise the blockchain, if they are produced too slowly, the chain would not grow fast enough, right? So, and we need to moderate that. So we need to be able to adjust the time to spend on the solution, both from below and from above, right? And we need to be able to do it dynamically. Context sensitivity means that the crypto puzzles, the useful tasks, needs to be connected, tied to the particular context or particular block. Because the idea is to prevent reuse, so we cannot take some past solution of the useful task and say, okay, we reuse the solution again. And we prevent it not by maintaining some database of everything that has been solved, but rather making sure that the instance of the useful task is derived from the context of the useful task. And the context would include the already existing chain of blocks and the list of transactions we want to include. So that's called context sensitivity, very essential. Similarly, non-amortizability. Non-amortizability means that if someone has been solving useful tasks for a long period of time, that someone would not gain any advantage compared to the newcomer. So it means that the cost of solving useful tasks would not be amortized over time. It's yet another property satisfied by crypto puzzles. Okay, if I spent all my year solving crypto puzzle and I don't gain any advantage compared to someone who starts today. Non-zero variability in the solution time. That's also very important because we don't want everyone to propose blocks at about the same time. That would create a congestion and branching. So we want significant variability in so if you look at the distribution of time, like how fast blocks are proposed, so we know the average. But it's not only about the average. There is significant variability in the time to propose a block. And crypto puzzles satisfy that. But many useful tasks do not. Okay, some of the properties are quite obvious. So we need to generate tasks efficiently. Well, if we need to train a model, it won't be an efficient task generation. we need to verify the correctness of the block and of the task solution efficiently. So task needs to be hard to solve, but needs to be efficient to verify. We already talked about the property of fairness. Fairness means that if I have twice as much resources as the other node, my chance to propose a solution needs to be not higher than twice the chance of that someone to propose a solution. So what we want is to prevent superlinearity in the dependency. So there is dependence of the probability to find a solution on the amount of resources possessed by a single node. In this case, we need this dependency not to be superlinear. That's important for fairness. It's another challenge. Another interesting one is blocks. We call it block switchability. What is block switchability? Suppose I'm mining the current block, and then someone managed to beat me to it and sends a proposal. So how much do I lose from switching from mining my current state of mining on top of the previous block to the new state of mining on top of the recently proposed block? So a very important property of crypto puzzles is that I don't lose. Well, of course, if I beat the other block, maybe it would be good, but I don't lose anything. I don't lose due to the if I have been mining on top of a certain block for a period of time, I have not gained any advantage. So if I switch to mining on top of another block, my probability to find the solution would not be reduced. That's a very important and nice property of crypto puzzles. It does not exist for many other classes of tasks, because mining can be a stateful process. If finding a solution for a class of tasks is a stateful process, then I've already been accumulating some state. Now if I switch to mining on top of a different block, I would be losing that state. So that's a problem. So when I switch, there should be no reduction in the probability to find a solution and no reduction in the expected time to find a solution. So you can see it's quite surprising how many different properties crypto puzzles satisfy, and that's essentially the reason why none of the many, there are quite a few proposals that explored, that came up with sophisticated technique to provide a certain property, but no proposal covers the entire spectrum of properties. So this is why the mainstream cryptocurrency system based on POW are still using crypto puzzles and not any alternative, not any useful task. So this is the end of the lecture. And I would like to thank you. It's actually interesting. Thanks for your attention.